So yeah, I don't know. So 2 weeks ago we did this thing where we used like topology to solve a combinatorial problem, which is like really cool. I think it's awesome when like different areas of math, like you can use one to solve a problem from another. But for a combinatorialist, that's kind of sad, right? Because it's like we come up with a problem, we can't solve it, and we need like a more developed area of pure math to be able to solve it. So this lecture is going to be somewhat of a kind of revenge in some sense. We're going to take a problem that originated in pure math, and we're going to solve it like completely with combinatorial methods. So, okay, here's a definition. It's kind of a definition. It's again kind of like when we did topology. We don't really need to care about anything deep about it. So I want to define a normed vector space, but it almost doesn't matter what it is in some sense. It just needs a few kind of basic properties. So a normed vector space is a pair V, comma, like norm function, where V is a vector space and I literally don't care what dimension it is. It could be infinite dimensional, it could be the real numbers, it could be, doesn't matter. It could be complex, it could be real, it could be maybe a finite, I don't know, yeah. That's not even, but it doesn't really matter what it is in some sense. V is a vector space, and the norm maps vectors. So this is like a function that takes vectors to non-negative numbers. And I'll just say it is a norm. And hopefully it's okay if I don't let's not go through all the properties of norms. For all intents and purposes, like you can think of V as being the d-dimensional kind of real space and this norm as being the Euclidean norm. In other words, just like the length of the vector. So a norm is a length function. The key things about norms are like they have to satisfy, the triangle inequality. Basically, is the main key thing. So at some point we'll sort of use the triangle inequality, but everything really does suffice to think of this case. But we're not going to use any special properties of the Euclidean norm or anything like that. So here's another definition. So we're going to be thinking of taking a bunch of points, Z1 up to Zn, in a vector space. And a subset of 1 up to n. And I just want to introduce some notation to talk about the sum of all the points Zi where I is in that set. So it's something called, we're going to think of it, maybe a word for that is like a subset sum. So just a shorthand, Z sub A be the sum over I in A of Zi. So we call this like a subset sum because it's summing over the points that correspond to indices in that subset. Okay. I think that's all I need to state the problem. Actually, but maybe let's do an example. Let's just think of the simplest case. V is the reals. So it's like a one-dimensional vector space. So in other words, it's R1, right? And say that, and suppose, Z1 equals Z2 ... equals Zn equals 1. So if I take a subset A, what's my subset sum going to count or be equal to? Yeah, exactly, right? Because it's literally just summing up the number 1 for every index that's in A, and there's cardinality of A such indices, right? But obviously, so this is a very simple case. All the things are the same. They're all equal to 1. If we're in a kind of high dimensional or even infinite dimensional vector space, this could be kind of complicated. You have all these vectors that add up and combine in very strange geometric ways. So yeah, it won't be so simple in general. OK, let's state the problem. So this is from 1943. So what they wanted to do is find the maximum it's like the assignment, right? Find the maximum, upper bound and lower bound, I guess. So find the maximum size of a family such that, so F is, collection of subsets of 1 up to n, like usual. And there exists some Z1 up to Zn in this vector space. So that's maybe for some vector space, try to solve, so such that, so the rule is that all of these vectors have to be length at least 1. And what we need is all the subset sums to be close to each other. So all the subset sums for sets that are in F. So to say two vectors are close in a normed vector space, that's like saying that the norm of their difference is small. And here, since all of our vectors have length at least 1, 1 is kind of my, 1 kind of defines whether a vector is big or small in some sense. So we want all these subset sums to be within 1 for all A, B in the family. It's kind of a complicated statement, we're maximizing the size of a family, but then so we get to choose the family, right? So you have the choice of the family, and you have the choice of the vectors. So I want to design these vectors, choose them in such a way, and then choose the family in such a way that these things are satisfied. It's their length at least 1, and they're close to each. The subset sums are close, and we want to make F as big as we possibly can. And yeah, like I said, this kind of looks like a mix of a combinatorial problem and some kind of pure math problem involving vectors or something. This actually came, though, from a paper on roots of random polynomials. And somehow what they were doing boiled down to this kind of question, which they were able to prove bounds on, but they were not able to solve. So they couldn't get the exact value for this maximum. But yeah, we're going to see how to actually compute the exact value. Any questions about this statement? OK. So shortly after, so a few years later, Erdős discovered that there's some connection between this and Sperner's theorem. And he used that to solve the case where the vector space is just the reals. So we're just in a one-dimensional world, and it boils down to Sperner's theorem. It still doesn't solve the whole problem, though. But let's see that proof, because it's kind of simple. Although it's still clever. I don't know how you would come up with this. So if V is just the reals, and of course the norm is then just the absolute value function, then the answer is n choose n over 2. This was also sometime in the 1940s. I think maybe 46 or something, 45. Anyway, a long time ago. Okay. So for a lower bound, actually for a lower bound, it kind of comes back to this example. Because I could just let all the numbers be 1. So and now, as long as F consists of sets that all have the same size, because remember, when all the numbers are 1, the subset sum just computes the cardinality of the set. So if we take sets of the same cardinality, then their subset sums are equal, so the difference is 0. So it'll satisfy the property. And definitely, I've picked the numbers to be 1, so they're all at length at least 1, right? That's the first condition here. And yeah, if I pick sets of the same size, then they have the same subset sum. So, and to pick sets of the same size, the best thing to do is to take F to be this n choose n over 2, right? And then, if I take ZA minus ZB, that's just the cardinality of A minus cardinality of B, which will just be 0 for any two sets in F. So, and 0 is less than 1, right? So this gives us a construction. Now we have to prove the upper bound. So yeah, I want to show no matter what the z's are, F can't be bigger than n choose n over 2, right? Here's one observation. What if all the numbers were positive? Just a very simple, like these in the problem, the z, so we're in the reals, right? So all the numbers, they're either going to be real numbers that are positive and are at least 1, or negative and at most negative 1, right? That's what all of our numbers are going to be. to have absolute value at least 1. So like, suppose the numbers were all positive, right? So it's kind of an ideal, I mean, might seem like it's unlikely to happen, but yeah, let's just suppose we're in this ideal situation that the numbers are all positive. Well, then I claim F has to be an anti-chain. In this case. And then we can just apply Sperner's theorem. So maybe it takes a bit of, we should do some thinking. Why would it have to be? So if I assume all the numbers are positive, what would have to be an anti-chain? Exactly. And like there's no cancellation between these things or anything because they're all positive. So yeah, so just to kind of write that kind of formally. So if you had A a strict subset of B, right? What would this thing be? Well, if I take ZA minus ZB, well, everything in A is in B because it's a subset. So this ZA completely cancels with the corresponding terms here. And you're just left with like Z of B minus A because, yeah, those terms cancel with those ones, except for the ones that are in B minus A. But yeah, all of these things are, so this is like, the sum I in B minus A of Zi. But all of these are positive numbers of, length at least 1. So this is going to have length at least 1, right? I'm just adding a bunch of positives. They can't cancel, right? OK, so like I said, this is kind of an ideal situation, but this connects to Sperner's theorem, right? So in this case where everything's positive, you definitely get that this is at most n choose n over 2 by Sperner's theorem. And it turns out if you have negative numbers in your list of numbers, then you can just do some fiddling. So actually, maybe. So now suppose so I guess so suppose there are some negative numbers. So while there exists an I such that Zi is negative, do the following. So I modify the family, and then I modify, so I'm going to just replace Zi with its absolute value to make it positive. So change Zi to like a positive version of itself, absolute value of Zi. So but of course that's going to mess up it doesn't mess up the condition that, so the absolute values of all the things are still positive or bigger than 1, but like it messes up the subset sums. But then I change my sets. So for each A in F such that I is in A, replace A with A minus I. And do the same thing for, well, do the opposite thing if it doesn't contain I. So if I is not in A, replace A with A union I. So I claim that this all this is going to do is going to take all the subset sums and shift them by the same amount. If I just take all the subset sums and shift them by the same amount, they're still all close to each other. So if you think about it, for the first case, like maybe I won't write things for this because I want to go to the general case. But originally this set A had I in it, which means it had, like, in the sum it had a Zi, which is a negative number. If I remove I from A, then the subset sum for A shifts positively by absolute value of Zi. It used to have a negative number in it. I took that negative number out. It goes up by absolute value of Zi. This one used to not have I in it. I've now put I into the set, but I've also changed Zi to be positive. So now the new sum for this set includes the absolute value of Zi. It shifts positively by absolute value of Zi. So every subset sum shifts positively by the same amount, so they're all close to each other. So every subset, I'll just say that in words quickly, shifts up by the absolute value of Zi, so the property is maintained. And then as long as you have a negative, you just keep doing this. Now they're all positive. Now it's a anti-chain, and now you win by Sperner. Okay. Is that clear? Any questions about that? Okay, so that's the real case, and that just boils down to Sperner's theorem. But now we're in like a crazy vector space of any dimension. And this kind of idea of just like things just shifting, like the thing is, it's nice when everything lies on a line. When you do things, you just know it. I mean, you know, it's a bit of a simpler situation. So now let's prove the general theorem. Okay, I think I can erase this, right? Oh, sorry? So the thing is, the Zi's are always going to have absolute value bigger than 1, or at least 1. So yeah, so it can't be actually 0. That's a good point. Yeah. Okay, so yeah, let's prove the general theorem. So the answer is always. So this is a theorem of Kleitman, I think from '66. So the answer is n choose n over 2 for any vector space V. Or I should say maybe V, any normed vector space V, absolute value, or sorry, norm, whatever. Lower bound is the same as before. So you just take a bunch of points that have length 1, and they all lie on the same line. And that'll be the same as before. So all we have to do is really prove the upper bound. In this case, it turns out that, in the previous proof, we boiled things down to applying Sperner's theorem. It's not going to really work in this case we can't just apply Sperner's theorem. At least I don't know any way to do it. But the smarter idea this time is to, instead of applying Sperner's theorem, just try to mimic the proof of Sperner's theorem using symmetric chains. But we need to change the idea of kind of anti-chain to something else and change the idea of a chain to something else so that it makes sense for this problem. So I want to think of my family F as kind of being like an anti-chain. So if you have subset sums that are close to each other, I think of that kind of like an anti-chain. And so a chain would be a collection of sets where the subset sums are far from each other. So,
John,
yeah.
for the construction, how do we deal then with the fact that you obviously can't take one for everything now?
So you just take any vector of length equal to 1 and just set them all equal to that vector. And then when you sum things, like there's not going to be any kind of like the length of the vector, the subset sum just depends on its cardinality again. Yeah. So let's kind of define a kind of notion of kind of like a chain, but in this setting. So say that a family D is separated if all the subset sums ZA, like they're all far apart. So if I take A and B in the family, then the two subset sums are at length or at distance at least 1, obviously unless A is equal to B. So for all distinct A and B in D. And I guess the key idea now is, well, if I take my family F and I take a separated family, they can only intersect on at most one element, just like with chains and anti-chains, right? If you had two elements in common, they'd be far apart. That contradicts the property of F, right? So I want to kind of make a sort of like something like a partition into symmetric chains, where chains become separated families. But now there's also not a really good notion of symmetric anymore. So I need to change that definition as well. So say that a partition so this is trying to generalize the idea of symmetric chains. So let's say D1 up to DS of the power set is, I couldn't think of a good name for this. So I'll say appropriately sized. If for each I between 0 and n over 2, the number of indices j such that the size of dj equals n minus 2i plus 1 is n choose I minus n choose I minus 1. So this is a real big kind of mouthful.
So this is analogous to the chain partition?
Yeah. So if we think about a symmetric chain partition, I want to say, let's just kind of verify a symmetric chain partition would have this property. So remember, symmetric chain kind of partition, like every chain starts on some level k, let's say, and goes up to level n minus k. So how many chains start at level 0? So they start at like the empty set. Well, if you start at level 0, you must go all the way up to the top. Right? Because that's the only way. If you start at the empty set, you must also include the whole set. And there's only one such chain in a partition. Oh, here I'm going to define, if I take n, choose -1, that's 0. Because that's actually coming up in this case. If I set I equals 0, so yeah, if you set I equals 0 in that thing, so you have, so there's n choose 0 chains of length n plus 1, because n plus 1 would be starting at 0 and going up to n, because n choose 0 is 1. So that kind of checks out. And then if I ask how many chains start at level 1, well, it's for every set of size 1, there has to be a chain that either starts there or started below and went through that set. So like the number that start on level 1 and end at level n minus 1 should be n choose 1 minus n choose 0. Because like this chain already hit that level, so I need to start a chain at every other point. And then the number that started at level 2 will be like n choose 2 minus the one that started below, which is n choose 1. Like below either here or even further down. So like the number of chains starting on any given level is like, you know, that n choose that level minus the ones that started earlier, which is the number of things in the previous level. That vaguely. Oh, and I should say the number of things that start on level I is equal to the number of families that have size n minus 2i plus 1. Because if you start on level I, you end at level n minus I. If you do the math, that's n minus 2i plus 1 elements. Okay. That seemed to kind of check out. So what we're going to try to do is try to find a partition of the power set into separated families that are where the partition is appropriately sized. Maybe we should show that that's sufficient first before, like, why would this work? Why would this, so suppose like 2 to the n has an appropriately, so I'll just say app sized partition into separated families. So then I do my usual thing where I say the size of f so this is a partition, so this is the same as the sum of I from 1 to s. So s is the number of families, just like on the other board, of f intersect ds, or sorry, di, which for every, this is always at most 1. So I get an upper bound which is equal to the number of families in the partition. So I want this to equal n choose n over 2. So sorry I'm going kind of fast through this, but I really want to get to like the punchline. So now I need to kind of compute how many, so if I had a appropriately sized partition, how many sets would there be, or how many families would there be? Well, for each I can compute the number of families of length or size n, n minus 2i plus 1, right? So I can just take, and that's going to be that. Right, so I'm just going over kind of all the possible sizes. So maybe this definition should have included that, like all the families have like one of these sizes, and the number of that given size is n choose I minus n choose I minus 1. But this is a telescoping sum. Right? Each term of the sum has a positive thing and a negative thing, and the negative thing of the next element in the sum is equal to the positive of the previous. So this just ends up equaling n choose n over 2 minus n choose minus 1, which was 0. So that's just n choose n over 2. So the key thing is that this telescopes. Do you know what I mean by telescoping sum? Is that's a thing you guys have heard, or? Yeah. So each term, the next positive term will just cancel with this positive term will cancel with the next negative term, and so it just clicks together like a telescope. So this proves if we had a partition of this type, then we win, right? Then the size of f is at most s, and s is just equal to n choose n over 2. Any questions about that bit? And yeah, it's again important that we've got this kind of duality between separated and separated families and F, right? Like F has everything, all the subset sums are close, and separated things, all the subset sums are far, so they can't intersect on more than one element, right? Okay, so let's get a partition like this. And you'll see in this proof that we need like something about norms, but it's like so minimal that it doesn't matter what the norm is, really. So we find the partition. So we find such a partition by induction on n. And this is going to be reminiscent of when we found a symmetric chain decomposition. We're going to do the same thing. Isolate the value, kind of take away the value n, find a partition for 2 to the m minus 1, and then try our best to like add in n in a sensible way to extend it. So for the case n equals 1, well, we just let d1 be the whole thing, and this is separated because, like, if I take z empty set minus z set containing 1, that's equal to, so the empty set, like, it just computes 0, right? So it's just the 0 vector. So this is just the length of z1, which is at least 1. So base case is easy. So now we do n at least 2. So let's say d1 up to ds be such a partition So separated families that are appropriately sized for 2 to the n minus 1. And I should also say, like, this also depends on, z1 up to zn minus 1. Right, because the separated property depends on the z's. But to be clear, we just ignore the number n and use induction. So what I want to do is exactly the same thing as we did in the proof of Sperner's theorem. Sorry, I just want to get things in the right order here. Okay, yeah, so let's, like I said, let's do things exactly the same way as in Sperner's theorem. So sorry, I can't do that yet. The thing is, like, these are not chains. In Sperner's theorem, it was important that we take for each chain, what we did was we took the top element of that chain, and we did like two different things based on, we did two different things. We either added the element n to that set and made a longer chain, or what we did was take that set out and add n to everything else. Those were the kind of our two operations. Here, like, these aren't chains. Like, what is the top element of D1? Like, there is no largest element, because these aren't chains. But we have to then, what we're going to do is kind of come up with a way of measuring somehow the largest set in D1 with respect to something to do with, so this is going to have to do with the norm now. So I'm going to define a function from the vector space to the reals. And here's how I define it. So if it's okay, let's kind of just roughly say what we're going to do. So you kind of project V onto the line span of Zn. And then for each like x and v, like f of x, we define it to be equal to the length of that projection, although, so like Zn points in some direction, right? So let's say so imagine we're in this vector space. Zn is a vector. If I take the span of Zn, that's a line. It goes off to infinity in both directions. What I want to do for each x in my vector space is so this is the origin here. What I do is I first project onto this line in sort of the natural way. And then I just map x to whatever the length of this is, although it's kind of a signed length in a sense that if x was over here, like I take the negative of whatever that length is, right? So, yeah. The length of that projection but it could be negative. I don't really know how to say that, right? I mean, if it's over here, it would be a negative number. Yeah. Is there a good word for this? I don't know, but I guess the important thing is that, is it clear what I mean by this? I basically want to think of this whole line as being the reals, like the real numbers, right? I just project onto that line, and I take whatever real number, like where this, would be the length of Zn, like that real number. I just take whatever real number I get by projecting onto that line. So like in particular, fZn will just be the norm of Zn, because I project onto the line and I take the length, which is just the length. But also geometrically, you can maybe see in this picture that f of x, because of the way triangles work, right? If I project this, the absolute value of this should be less than the actual length of the vector. So if I take the norm of, the norm of fx is at most the norm of x for all x in V. And f is linear. So these are kind of three properties I need. And if you think about it, if you do take the sum of two vectors and apply this operation, you'll get the sum of the result will be this, it's going to be linear. Basically, projections are linear, right? Any questions about any of this? Okay. So this is the way I'm going to judge what is the biggest set in D1. It's going to be whatever set has the biggest f value when I take the subset sum. Yeah?
For the final projection, do you need an inner product, or can you do it?
Yeah, that's a good question. I might be being a bit loose with with everything going on here, but basically, I just want a linear function that satisfies these three properties, and maybe I won't prove that like such a linear function always exists, but yeah, essentially that. I mean, do you need an inner product? You might. I don't know, But basically, yeah. So let's just assume that such a linear function exists that has those properties, and then that's kind of a technical detail just to check. Okay, so So for each j, I'm going to pick aj and dj so that this function on that subset sum is maximum. And then I'm going to define, like we did before, dj prime will be, it's the set of all, it's the original kind of chain I had before, and then I take aj union n. dj double prime is the set of all b union n, such that b is in dj and b is not equal to aj. This one here is easily seen to be separated. Okay. We also need, we need appropriately sized and separated. Maybe I'll just, because we are running out of time, we've kind of run out of time. But appropriately sized comes from Pascal's theorem, or identity. But the interesting part is showing that this is separated. So y, if I take two sets in here, then they definitely have the property because it inherits the property from dj. So it's just if you have a set here and a set here, like that's the only issue. AJ union N and something that was in the original family. So I'll just quickly say then, so if I take B in DJ, all I have to do is look at this difference. Property of my function, this is at least Z of, so yeah, sorry, I'm just kind of scribbling this down quick. But by linearity, this is just f of ZAJ minus f of ZB plus f of Zn. But this is so this is the biggest one, so that's at least that. So that kind of cancels out. I just get f of Zn, which is the norm of Zn, and that's at least 1. So it is separated. Okay. Like I said, the appropriately sized property comes from using Pascal's identity in the right way.